Okay. All right. So, hello everyone. Welcome to the PC seminar. And we have with us today Siddharth Gupta from Ben-Gurion University from Israel. And he'll be talking on parameterized complexity of finding subgraphs with hereditary properties on hereditary graph classes. So, thank you so much for joining us, Siddharth. Over to you now.
Okay, thank you, Fatima, for the invitation. So I will be talking about finding subgraphs. So the main problem is finding subgraphs with hereditary properties on hereditary graph classes. And this is a joint work with my PhD advisor David Epstein and one of my um, students, one of my students from my PhD lab, Aram. So yeah, so I'll start. Okay. Yeah, so I'll first briefly go through what is an hereditary property. So for this talk, we say that a graph property pi is hereditary if it is closed under taking induced subgraphs. And some examples of hereditary properties are if you have class of planar graphs or class of triangle-free graphs. So if a graph is planar, then if you take an induced subgraph of that graph, that is also planar, and that's also true for triangle free graphs as well. So for this talk, what we do is we take we take an hereditary property and we partition them based on based on the number of cliques they have or the number of independent set they have. So we say that a property is SA if it excludes some complete graphs but includes all independent sets. So, as for example, if your graph is planar or bipartite, then in case of planar, it excludes complete K5 or above all the complete graphs, but it includes all the independent sets. And same is true for bipartite, where you don't have any complete graph from K3 and above. Similarly, we have AS. So the first letter denotes whether you have all complete graphs or some complete graphs, and the second letter denotes whether you have all independent set or some independent set. So AS means that you have all complete graphs, um, but you have only, sorry, it should be, yeah, so it includes some independent set, and if you have SS, that means you exclude some complete graphs and some independent set, and AA means that you include all complete graphs and all independent sets. Okay, so then what is the main problem? So the main problem, which is we denote, we say this is subgraph finding problem. We have a graph G and a hereditary property pi, and you have an integer k. And the problem P of G pi k asks whether there exist k vertices of G that if you take the induced subgraph on that, that satisfies property pi. So this is the original problem, and this was proved to be NP complete by Lewis and Ian Cassis in 1980. And in 2002, Cote and Raman studied the parameterized complexity of this problem, and then they proved that it is W1 complete if pi belongs to either AS or SA, and it is FPT otherwise. So now what happens? Then then we were thinking that what happens if we restrict our input graph classes for when your pi is either AS or SA. So like one example is if you see that K clique is W1 complete for general graphs, but it's FPT on multiple interval graphs. So on the same theme, we study that if I restrict my graph input graph class, what happens? So can we give a fine-grained view on this for this case? So then that's why we define this new problem that's called restricted subgraph finding problem. And sorry, yeah, so now what we have is an input graph G, and now we have instead of one, we have two hereditary properties. One is for pi G and one is pi, and we have an integer K. And now the problem asks whether there exists K vertices of G that induces a subgraph that satisfies property pi. But now we have a condition that so our input graph G is not any graph, it belongs to a hereditary graph class pi G. So this is the problem. I think is the problem clear? Yes. Okay. So now what we do in this paper is we establish a framework which settles the parameterized complexity of this problem for various hereditary graph classes. So in our paper we heavily use Ramsey numbers. So first, what is Ramsey number? That if I give you two positive integers p and q, then um, if so, what we say is that any graph of size r of pq, which is we call that Ramsey number of p and q, it contains either a clique of size p or an independent set of size q. So then how large? So how large is this number? So R of PQ is at most P plus Q minus 2 choose Q minus 1. So this is called Ramsey number. And now we have some practicability results in our paper. So we'll first go through them. So the first case which we consider is when your pi g is belongs to AS. That means it has all the cliques, but it excludes some of the independent set. And your pi is SA, so it has all the independent set, but it excludes some of the cliques. So then we prove that this problem is in polynomial time. So some of the graph classes which are covered by this meta theorem is when your pi g is co-bipartite and your pi is either a forest or a planar graph or bipartite or triangle free. So so assume that okay. So if I how do we prove this is, let's say um, I of pi g is the smallest independent set, which does not belong to the hereditary of class pi of g, and similarly, c of pi is the smallest clique which does not belong to pi. So now, if you see that if my k is greater than or equal of r of c pi and I pi g, then if I take any induced subgraph of size k, then it will either have a clique of size c pi, or it will have an independent set of I pi g. So if I restrict the induced subgraph to be like if I restrict the graph to be an induced subgraph of G, then we know that G does not have an independent set of size I pi G. So that means that every induced subgraph of size K will have a clique of size C pi. And that means, and as you can see that pi does not have if a graph belongs to pi, then it cannot have a clique of size c pi. So that means that G does not have any k vertex into subgraph which belongs to property pi. So then we just return no to this problem. And then if my k is less than r of c pi and I of pi g, then you can just brute force to test. So that's why. So now if we look at the running time, so then we can see that so what I do is I take every k vertex, I choose k vertices of G, and then I check the edge. So I check the adjacencies between them, and I get the induced subgraph on those vertices, and then so if this t of pi k is the time to test whether a given k vertex graph has property pi, then you can see that the total running time is this much. And then because k is bounded by r of c pi and I pi g, so then we get this running time where r have this value, and then you can easily see that because the c pi and I pi g are both dependent only on the properties pi g and not on the input graph. So that means these are, once you define pi and pi g, then this r is a constant. So you get a polynomial time algorithm. But so although it is polynomial, my r can be huge because it's dependent on this Ramsey number. So then if you take a subclass where you say that my pi g still belongs to AS and pi belongs to SA, but now my induced so if the induced subgraph isomorphism is in FPT for pi g, then we can get rid of the exponent and we can get a better algorithm. So an example of such a graph class is that if your graph class is planar or in general a no dense graph, then the induced subgraph isomorphism is in FPT. So now in this case, you can see that what we can do is we first take all the so we generate all the k all the graphs of size k, so that is so the number of graphs of size k is this many. And then what we do is we simply, for each graph, we check whether that graph satisfies property pi, and as well as that graph satisfies property um, um, pi g as well or not. So if it satisfies both pi and pi g, then we return yes, otherwise we return no. And then in this case, you can see that we get so we get rid of the dependency of R on N, and then basically this T of pi of R is with respect to pi, and then similarly you have this FPT running time for a subgraph isomorphism for pi g. So this particularly says that if your graph is planar, then you can just then this problem can be solved in linear time if your pi is an SA property. Okay. Okay, so now we go to the next case where when we say that both my pi g and pi, they both belong to AS. That means they include all the cliques but exclude some of the independent set. Or the similar cases when they both belong to SA, and then this problem is in FPT. So some of the examples, known graph classes which are covered by this theorem is when your pi and pi g are both planar or bipartite or triangle free, then this problem is FPT. Okay, so how do we prove this? Is if both pi g and sorry, this should be just pi. So if both pi g and pi belongs to AS, so we'll just consider this case. The other case is similar. And then you can see that if the size of my graph G is more than R of K and I by G, then G either have a clique of size K or an independent set of I by G. But as we know that this property pi of G is AS, so it does not have an independent set of size I by G. So that means G has a clique of size K. So now in this case, we just return yes. And in the other case, if my so that means that my input graph has bounded size, and then I can just brute force. And then in this case as well, just the running time is same, that in choose k, and then you do this is to create the graph, induce graph, and then this is to check whether the graph belongs to property pi, and then we also get FPT time. This case, okay. And now we go to a case where my graph pi g belongs to SS. So then it is very easy to see that the problem is solvable in polynomial time. So why? Because SS means that you exclude some complete graph as well as exclude some independent set. So let C of pi g and I of pi g be the minimum clique size and minimum independent set size, such that they don't belong to property pi of g. Then we can easily see that my graph is bounded by Ramsey number of C of pi g and I of pi g. Why? Because otherwise G has either a clique of size C of pi g or an independent set of size I pi g. So this also gives us polynomial time algorithm for this problem. Okay, so Yes, now we'll go to the hardness results. I don't know if anyone has any questions. Everything is clear. So I cannot see the chat. Pratibha, is there any
Yeah, yeah,
questions?
yeah. I'm keeping an eye on the chat. There are no
Okay,
questions yet. I'll let you know if
okay,
there's something.
okay. Yeah, thank you. So now we'll go with the hardness results. So now so we'll use two definitions here. So we'll first introduce what is strong products. So in particular, we use strong products with cliques. So in general, if I give you two graphs, the strong product is basically that you put up. So let's say if you have you take the product of Cartesian product of the graph G and vertex set of G and vertex set of H, and then you add an edge between two vertices if their first coordinate is same or their second coordinate is same, and then at the same time their second coordinates make an edge in the other graph, or both their first coordinates and the second coordinates make an edge in the second graph. Okay, so in particular, when you do a strong product with cliques, you can either follow the same definition, or there is an easy way to see this is when you let's say I have a graph G and I have a complete graph in case K3, then the strong product how you can create is first you replace every vertex with the clique of basically, so whatever is the clique size, so in this case K3, and then what you do is if there is an edge between two vertices in G, then you add all the edges between those cliques. So in this case, I have an edge between A and B, so I add all the edges between the clique which corresponds to A, and similarly I add all the edges, um, and similarly I have an edge between A and C, so I do the same. So this is an easier way to look at when you do strong products with cliques. So now, if you remember, so the only case that is remaining is when your graph class pi g is belongs to AA, and then so here we see both kind of results. So there are results, there are graph classes for which the problem is polynomial time, and then there's also FPT, and then there are problems which are W and half. So we cannot get the results similar to what we got in the previous cases. So here we give some conditional results. So now the first results says that if your graph pi g belongs to AA, that means it has all the cliques and all the independent sets. And if it is closed under strong products with complete graphs, so that means that if I do this, so if a graph G belongs to AA, and then if I do a strong product with any complete graph of complete graph and G, then that also belongs to pi G. And my and the property pi belongs to SA. And then there's another property which says that any disjoint union of K of chi pi belongs to pi. That means where chi pi is the maximum chromatic number of any graph G in pi. So that means if I take any disjoint union of these clique size, then that should also belongs to pi. And if these conditions are satisfied, then we say that my problem is as hard as this problem where I replace the property of pi with just independent set. So that means um, checking whether graph G has a k vertex induced subgraph which belongs to pi is as hard as whether checking whether my graph G has a k independent set of size k or not. So I will first give some examples because this seems like a lot of conditions, but we get we get meaningful graph classes for which these conditions are satisfied actually, and as far as we know, those for then the problem was also the status of the problem was not known. So if I take pi g as the property of either being a unit disk graph or C4 free graphs or K14 free graphs. And I take property pi as say property of being planar or bipartite, then we know that for these graph classes, checking independent set is W1 complete. So that implies from our theorem, and combining this result implies that for our problem for these graph classes, and the problem is also W1 complete. Okay, so so we'll first so I'll first so I'll show first to the reduction. So then so we start with the problem where I want to find an independent set of size k in graph G, and we create a new graph G prime, which is basically the strong product of G and a complete graph on on chi of pi many vertices, and my k prime is k times chi of pi. Okay, so then just an example, let's say your chi of pi is 2, then my k prime is just 2k, and then okay, so what we do is, so you can see that if my g is this, then my g prime will look something like this. So um, an easier way to say is, so because my the clique which I took strong product with as size 2, so what I did was I just replaced every vertex with an edge, and then I just added the corresponding edges between those cliques. Okay, so then now we want to prove that if G has an independent set of size k, if and only if G prime has an induced subgraph of size k prime that belongs to pi. So first assume that we have an independent set of size k, then it's what we can do is you can easily see that, okay, if I have an independent set of size k in G, then every independent set will just give me a clique of size k of uh, k of chi pi, and then because the independent set has size k, so now on in G prime I get k disjoint copies of this complete graph, and as we know that pi includes all the disjoint union of cliques, so that means that we are sorry, we are done, because um, this is the required induced graph, and the size is also k times chi of pi. Okay, so now for the other direction, suppose that x is an induced subgraph of G prime of size k prime, which satisfies the property pi. Okay, so now this is, as we know that if I give you a graph x on n vertices, then there exists an independent set of size at least n over chi of x, right? So if I sorry, so this should be x. So then by using this property, then we know that x has an independent set I prime of size k prime over x of pi. So which is, that means that x has an independent set of size at least k. And now what we need to prove is that this, let's say this independent set I prime, first of all, that it has at most one copy of each vertex in G, because if it has more than one copy of a vertex in G, then we know that every word and the copies corresponding to any vertex in G makes a clique in G prime. So that will contradict that I prime is independent. So that tells us that I prime include at most one copy of each vertex in G. And then so now if I look at the corresponding set in G, then we can see that it is also independent in G. Why? Because if there was an edge between two vertices in G, that will also reflect in G prime. So that means that the the set which was corresponding to I prime in G is independent and has size at least k. So we get that G has an independent set of size k, size at least k. So that proves our theorem. And now we have another hardness proof which uses joins with peaks. So just recall that when we take joint of two graphs, what we basically do is it's we first take the disjoint union and then we just add the edges between to the two vertices. So first I took two copies of K3, put it here and G, and then we just add edges between every vertex of G and every vertex of every K. So this right. So we get um, so this is basically joins with peaks. And then now our second hardness proofs has this property. So we say that let's say my pi belongs to SA and pi includes all the subgraphs which are of type I plus t times a complete graph on omega of pi minus 1 uh, vertices. So basically where omega of pi is the maximum peak size of any graph. So you can see that if I see this graph, then this graph has a clique size of omega of pi. So that condition is satisfied. So we say that if pi includes all the subgraphs of this kind, and then so basically if I look at an independent set, then and I have complete graph on this side, then you can see that this complete graph and with this independent, with every vertex of independent set, I get a clique which is of size omega of pi. Okay. And then now if my pi g is closed under joints with disjoint union of cliques, and if pi g belongs to AA, so if these properties are satisfied, then we have similar result, which says that our problem is as hard as finding an independent set of size k in graph G. So then again, an example is if you want to find a k vertex bipartite induced subgraph of K1 3 bar free graphs. So then we didn't find any. So unfortunately, this problem K independent set is I guess FPT in for this graph class, but it does give so this does not give a hardness with respect to parameterized domain, but it gives us hardness in the normal sense, which says that because the k independent set problem for this graph class is and known to be NP complete, so this problem is also NP complete from our theory. Okay, so now I'll show the reduction. So the now how we construct this new graph G prime is we take the join of G with the R disjoint copies of complete graph on C vertices. So what is C? C here is um, this omega of pi minus 1, and R is this Ramsey number on omega pi plus 1 and k, and my k prime is k plus R times C. Okay. So now we again want to prove the same thing, that if G has an independent set of size k if and only if G prime has an induced subgraph of size k prime belonging to. So now if you see, if I take independent set I of size k in G, then if I take this graph, which is k plus R times k of complete graph on C vertices, then we get this as an induced subgraph of G prime, and then you can see that this complete graph has maximum clique size, it's omega pi minus 1, and I, I just showed that if you take a join with an independent set, then the maximum clique size of your graph is omega pi. It just increases by 1. So now you get omega pi, and as pi includes graphs of these classes. So this is a required graph class, and this also satisfies the size condition, which is k plus r times c. Okay, so let's say for the other direction, now suppose that again x is an induced subgraph of G prime, which has size k prime, and it belongs to a property pi. So then what we can do is we can take the vertex set of x and we can partition it into two sets, S1 and S2, such that S1 is a subset of vertex set of G, and S2 is a subset of this disjoint union of peaks, right? And then we can see that they cannot intersect, and then it can be easily seen that the size of S1 is at least k, because even if you take even if you have this whole graph, this all the disjoint union of peaks in your x, then it should be r times c here. So then the size of S2 can be at most r times c, and then because x has size k prime, so that we know that S1 has to have size at least k. Okay. So now the first case, if S1 is an independent set, then we are done, because that's what we require, that G has an independent set of size k. And now assume that S1 is not an independent set, then let UV be an edge that is in S1. And then you can, as we can see that we can again restrict the size of S2 by R times C minus 1. Why? Because from each clique, we can take at most C minus 1 vertices. Why? Because let's say if I take the whole clique C, and then there will be C vertices, and you have two vertices U and V here. So, and there's an edge between U and V. So that clique on C vertices along with this edge UV will give us a clique of size C plus 2. And then that means we get a clique of size omega of pi plus 1. And then, which cannot happen because x is a graph which belongs to property pi. So then that means that my S2 has size at most r times c minus 1. So now from here we can easily see that my S1 has size at most at least k plus r. And as we can see that what is my r? R is my Ramsey number on omega pi plus 1 and k. So that means either S1 has a clique on size omega pi plus 1, but then that cannot happen again because S1 is a subgraph of X. So that means that S1 has to have an independent set of size K, and that again gives us that G has an independent set of size K. Okay, so these were the results which we proved, and then so let's conclude. So what we did was we basically took the case for the general problem where when it was W1 complete, and then we narrowed down the parameterized complexity. And then, so then the results which we give also, so as a corollary, we get many well-known graph classes for which the problems get settled. So we think that the results are interesting. And then still, obviously, there's an open problem. One obvious open problem is that if you can get the parameterized complexity of the problem when my input graph belongs to AA without any restriction. So like as we know that this is not possible because we have all kind of results here. So maybe with less restrictions than what we have in our paper. And then obviously this problem is also interesting to study this like meta problem when under some other graph parameter. Okay. That's all. Thank you.
Okay, thank you, Siddharth. I guess we have some time for questions. So if there are any questions, we can You can just unmute yourselves and ask, or if you prefer, you can type in the chat.
So I have a question, Venkatesh here.
Yes.
So the third item in your open problem, is there an example you can point to where pi g belongs to AA, but an specific graph class where you know something or you don't know anything?
I don't have a specific graph class, but like what we think is the restriction which we give does cover some known graph classes, but I think there's still scope of improvement that maybe we can um, reduce some of the restrictions and maybe can cover more graph classes. But as of now, I don't think I have a graph class in mind.
For example, caudal graphs would be an example of an AA, right? Because it has all cliques
Yes.
and all independent sets.
Yes.
And so what is the kind of question then you are asking given a graph?
So
What about, okay, G, where does it belong to?
so caudal graph is your graph G, right? Because pi G is, so you want a k induced subgraph of a caudal graph, which is say, so my pi, so the pi has to belong in SA. So say if I want to get
Okay, so pi has to be in SA, okay.
yes. So let's say if I want to find k bipartite graph on caudal graphs, right? It's because
Hmm.
so, but I'm not sure if that is.
Yeah, okay.
Mm, yeah.
So is that the kind of question? I mean, so we
Yes.
don't.
Yeah. So yes. So those kind of questions are. So if assuming that it is not closed under the operations which I just mentioned, then yeah, we don't know. Like that question is not covered by the results which we give. Because if the so what I mean is caudal graph is AA, but our results only hold when the input graph class is either closed under joins with disjoint union of cliques, or with if I take a strong product with cliques. Sorry, is it clear?
Yeah. Okay.
So like in this, so if I go back. So in these graph classes, so like unit disk, if you take a disjoint, if you take a strong product, if you take a unit disk and do this operation that every vertex uh, you you replace it with a clique, and then take the add the edges between the cliques, the corresponding the clique between the cliques corresponding to the vertices, then you still get a unit disk graph. So um, so that's why we could use our theorem for this graph class.
But you may not get a caudal graph if you do this operation on each vertex, something, right? Hmm. Okay, that's why it's not
Yeah.
covered
Yes.
by this general result.
Yeah.
Any questions? All right, I guess there are no more questions. So let's conclude here. Thank you once again, Siddharth, for the great talk. It was really nice to have you. And thanks to the audience. Thanks to the audience for being around. And we conclude our session for today here and see you all next week. Thank you. Bye.
Thank you. Bye-bye.